Hello, everyone. I am Duwen Chen, a master's student in the School of Communication and Electronic Engineering, East China Normal University. I'm very glad here to introduce you our recent research at CVPR 2023, MagicNet, Semi-Supervised Multi-Organ Segmentation via Magic Cube Partition and Recovery. In recent years, semi-supervised learning has shown great potential to handle the scarcity of data annotations, especially in the medical image field. The left figure shows a simple method for semi-supervised learning. Both labeled and unlabeled data are firstly fed into the network. For labeled data, their outputs are supervised by ground truth, and for unlabeled data, sharpening or one-hot operation is done on their predictions to obtain pseudo-labels. The right figure is a typical paradigm of semi-supervised learning, which consists of a student network and a teacher network. Our method is designed in this architecture. Different from the left figure, pseudo-labels in the mean teacher framework are generated by teacher network. And the teacher network is updated via weighted combination of the student network parameters with exponential moving average EMA. In semi-supervised learning, labeled and unlabeled images are always thought to be from the same distribution. However, due to the limited number of labeled images, it's hard to estimate the precise distribution from them. The estimated distribution between labeled and unlabeled images always suffers from mismatch problems, and this is even largely increased by multiple organs due to complex anatomical structures of the organs, as the right figure shows. Thus, we start from a key perspective that fixed relative locations and variable sizes of different organs can provide distribution information where a multi-organ CT scan is drawn. We treat the prior anatomy as a strong tool to guide the data augmentation and reduce the mismatch between labeled and unlabeled images for semi-supervised learning. Here is the overall framework of MagicNet, consisting of a student network and a teacher network with two branches, cross-image branch and within-image branch. The details will be illustrated in the following sections. Firstly, assume that we have one labeled image and one unlabeled image. The two images are partitioned into small cubes with the same sizes, and these cubes from the two images are randomly mixed to original size while keeping their original relative positions in their original images. Then, these segmented images compose the branches of our method. After they pass through the segmentation network, their predictions needs to be recovered to the segmentation map that corresponds to the original image. Ground truth and pseudo-label are supervisory signals for labeled and unlabeled images, respectively. Since the teacher network takes the original volume as input and pays more attention to learn large organs in the head class, the teacher pseudo-label may be biased to large organs. This module is proposed to unbias the pseudo-label via blending cube-wise features. Specifically, we collect the number of voxels for each organ class as organ-wise weights during the training process. And we leverage these weights to blend the outputs from teacher model and within image branch as the final pseudo-label. As shown in the right figure of weighted map, on the one hand, we keep the pseudo-label of small organs if teacher outputs belong to small organ class. On the other hand, we remedy the possible incorrect pseudo-labels of big organs via changing them to small organ classes if omega m is large. This can effectively increase the chance of the voxels predicted to small organs. We conduct large amounts of experimental analysis to validate the effectiveness of our approach. For the design cross-image branch, we can observe that keeping position can achieve better performance than scrambling position. This demonstrates the importance of location priors in multi-organ tasks. And our cross-image operation between labeled and unlabeled image also makes their empirical distribution more closer to each other. For our pseudo-label refinery module, it performs better than teacher outputs as pseudo-label, and the outputs of cross and within branches are mutually supervised. Our approach noticeably outperforms state-of-the-art semi-supervised medical image segmentation approaches on both BTCV and MACT multi-organ dataset, with +7% DSC improvement on MACT dataset with 10% labeled images. Please refer to our paper for more details. Thanks for your listening.